Today, we have a special guest for you, Professor Yontae Chan from National University of Singapore. He's a good friend of mine, and he is a leading expert of small molecule imaging. Professor Yontae Chan, please show up. Then welcome to Kyoto.
Hi,
so he's going to tell us more about small molecule bioimaging.
Hi everybody, my name is Yontae Chan. I'm from Singapore. So we are working on the small molecule probes, and I'm going to talk about the bioimaging using small molecules. Here are the one problem for everybody. So this is the cell culture from the brain. Inside this the cell culture, there are neural stem cells. Can you find those neural stem cells? Without the proper sensor or probe, it's very difficult to see which one is the nucleus or whether which is live cells or dead cells. So our goal is by adding small molecule the probe inside here, and we wanted to show this is neural stem cell. So then by overlapping those images together, now we can visualize this kind of a small the neural stem cell. That is how we use small molecule for bioimaging. If chemists wanted to design this kind of a sensor, conceptually, most likely, you can make one binding motif and also one reporter motif together and then connect. And then, if the target molecule binds to this binding motif, this binding event somehow affects this reporter motif, and sometimes it can change color or maybe increase fluorescence, decrease fluorescence. So this is the concept of the probe design. So from the beginning, you know which is your target protein. That's why this kind of approach is called as target-oriented approach, or sometimes it is called as a hypothesis-driven approach. But sometimes, if you don't have idea about your target, you cannot use this kind of approach. That's why there is another kind of approach, so-called diversity-oriented approach. In this diversity-oriented approach, they make huge numbers of molecules, which is called as a library, and this molecule is a conjugated organic molecule. That's why they can absorb the light, but by this conformational flexibility, they lose their energy. That's why in the beginning, this molecule is not fluorescent, but only after it binds to this target protein, its total structure becomes rigid, and this molecule has much better chance to be fluorescent. So using this kind of approach, even in case you do not know about your target, still you have a chance to find proper probe molecules. As this one is based on discovery, and then we can move on. That's why this kind of approach can be called also discovery-driven approach. For example, this kind of molecules, so-called diversity-oriented fluorescence library, and it has a huge numbers of molecules. And let me show you one plate. And this size of a plate, it can be 96 or it can be 304 are the well plate. And using this kind of a plate, we can accelerate those screening. And then maybe this kind of a chip at the box. This is the black box with a UV lamp on top. And then you can put the camera on top. Then it's a very easy the screening system. Then this is without your target. And this is with your target. And then you can take picture and compare those two pictures in Photoshop program. Then you can find the proper sensors very quickly. Of course, there is some very expensive the plate reader type of the machines. And in this case, this machine is higher performance, but of course, it's a more expensive ways. Let's say, for example, in the coffee. In the coffee, there are several different other components inside, but one of the most important components in the coffee is the caffeine. Because of the caffeine, we drink coffee, then it can awake our brain. But time to time, too much caffeine is a problem for some people. It can be a pregnant lady, or it can be the children. It's not recommended to take too much caffeine. Or some people has an allergy to the caffeine. That's why if you go to the Starbucks, then you may want to order the cafe coffee, but sometimes they can make a mistake, and they give you just a regular coffee, but 10 minutes later, if they say, oh, it was a mistake, sorry, but it's too late. So that's why we thought maybe a caffeine sensor, which can be used in daily life, can be an interesting project. In that case, if you wanted to make this kind of a caffeine sensor, one approach is using that camera box, you remember? So this is without caffeine, this is with caffeine, and then take pictures, and then find out with caffeine, if we change colors into orange color, then maybe this kind of molecule you may call caffeine orange. Of course, by using spectrophotometer or the spectrophotometer machine, if it is dose dependent or concentration dependent increase you can see, then this kind of material can be publishable material. But real life application is not easy using this kind of spectrophotometer carrying to the Starbucks. That's why we spent half more year to make this into really useful material. And the final format is this kind of green laser pointer. With only green laser pointer, this is a decaf coffee and this is the regular coffee. If the coffee has enough amount of caffeine, it shows you orange color. And if it's the low amount of caffeine, like a 5%, then it just shows you green color by scattering. Different kinds of the coffee from different shops, or maybe the Nescafe or cappuccino, with sugar or milk. All of them, they just shows all red color. If they are decaf coffee, regardless of where they are from, all of them shows you the green color. In this level, then maybe you can say, if it's green color, go ahead, you can drink. If it's red color, then stop, think again whether you can drink it or not. So this level of the useful sensor development is kind of our purpose to make the useful sensors.